So chapter 17 is pretty much a continuation of chapter 16. We will still be doing ice boxes, talking about equilibrium of acids and bases. In the end, we will be adding acids and bases together in something called titration. And then we're going to be learning something called KSP. It's solubility product when a salt dissolves. Okay? So first, let's look into something called the common ion effect. So let's look at the word. If they have a common ion, there will be an effect, okay, in the acidity. Let me show you an example. In beaker 1, I have water only. Draw a beaker, okay. And in beaker 2, I have a salt. Okay, so this is a salt. It is sodium Na+, and this is acetate, C2H3O2-. This is a strong electrolyte because I know that sodium is in group 1. It'll dissolve 100% of the time. So you're going to get a lot of acetate in the beaker. So in the beaker, we have some Na+ and some C2H3O2. That is the acetate ion. Okay? Okay, so this one is just all water. This one has a salt in it. What we're going to do is we're going to add acetic acid to the beaker. Okay, so acetic acid is HC2H3O2. When that goes into water, it dissociates into two ions, H+ and C2H3O2-. Okay? HC2H3O2 is pretty weak, so you're not going to get all of it dissociating, but you will get some. Also, acetic acid can be written as CH3COOH. They are the same thing. So sometimes they're going to write this as CH3COO and then Na. Sometimes they write it like that. It's not, I mean, just make sure you understand that it's the same thing. Okay? I'm sorry, they put the Na in the front. NaCH3COO-. Okay? So, we're going to get the pH of this. And what do you think? Well, so it's a weak acid, so, you know, it can't be that low. So maybe pH of 3. 3 pH. Okay? So now we're going to add to this, we're going to also add drops of acetic acid as well. HC2H3O2. Okay, so when it falls into the beaker, what's going to happen is it's going to see this ion already there. So what's going to happen is instead of dissociating, it will stay together. Okay, so the reason this happens is, of course, water is already hydrolyzing, or water is already solvating all these ions. And if you add more, there's not much room for it. Okay, so when you add acetic acid, it's going to say, oh, sorry, somebody's already in there. Therefore, this acid will stay together. Okay, so instead of it being pH 3, let's say you added the exact same amount, it's not going to be pH 3. It's going to be not as acidic, maybe pH 4. So what just happened here? What you have is a common ion. So this is common to what's already in the beaker. If there is a common ion inside the beaker already, what it will do is it will prevent the acid from dissociating. So they stay together. Okay, so if a common ion is present in a solution, the equilibrium will shift to the left. So it's going to go back to the acid form and not break apart to counteract the added ions because you already added some of these ions. Okay, so the acid becomes even weaker. Instead of it being pH 3, it's pH 4. Okay, you don't get much H+ produced because it's still stuck on there. So when a weak acid, like vinegar. This is the same thing as this is acetic acid. And you have a strong electrolyte. This is the salt. That strong electrolyte means they break apart 100% of the time. It contains a common ion. So the common ion would be the acetate ion here and the acetate ion here. Okay? The weak acid ionizes even less than it would if it were alone in solution. That's called the common ion effect. Okay? So let me do an example. It says, what is the pH of a solution by adding 0.30 molar acetic acid? Okay, so you're going to add acetic acid. So acetic acid is HC2H3O2. And it's going to dissociate H plus and, of course, equilibrium. H plus plus C2H3O2 minus. Another way of writing this is CH3COOH, equilibrium, H plus, and CH3COO minus, the same thing. Okay, so I'm going to go ahead and box this so I don't get confused. So it says, what is the pH of a solution by adding 0.30 moles of acetic acid? So you have 0.30 moles of this and 0.30 moles of sodium acetate. Okay, so when you take, this is confusing, okay? Sodium acetate is NaC2H3O2. Because it's a strong electrolyte, you can pretty much know that it's 100% dissociation, and sodium is not going to change. It's not common to anything, so it's not going to do anything. So you're just going to assume that this 0.3 moles is pretty much just this right here, the acetate, because the sodium won't do anything. So I'm going to write 0.3 moles in here. Okay, so what you have in this beaker is a common ion, okay? And you have to make 1 liter solution. 1 liter, 1 liter. Okay, so the molarity here is pretty much, I'm going to draw an icebox. So this is pretty much 0.30, and this is pretty much 0.30. Okay, so you don't have any of these because it didn't say that you had any acids or anything. So you're going to do minus x plus x plus x. So it's going to be 0.30 minus x, x, and 0.30 plus x. Okay, so before you just had in the beginning, last chapter, you just put a 0 there because you didn't have any common ions. But now you do, so you just put 0.30 right there. Okay, so then you're going to do the equilibrium expression. Ka of acetic acid is 1.8 E negative 5. 8 E negative 5 is equal to, so let me just write the formula. Ka is equal to H plus times C2H3O2 O2 minus over HC2H3O2. Sorry, that's really small. Okay, so Ka is 1.8 E negative 5. This is H plus, so you're going to do equals to X. This is 0.30 plus X. Knowing that this is lower than negative 4, we're going to make this negligible. And we will check the percent ionization in a minute. 0.30 over, make this negligible as well. So divide by 0.30. Okay, so X is equal to, that pretty much cancels, 1.8 E negative 5. Okay, to make sure that our assumption is correct by making that negligible, I'm going to do percent ionization really quickly. It's equal to 1.8 E negative 5 divided by the original, which is 0.30, times 100 hoping that it's less than 5%, otherwise I will have to do the quadratic equation, and that is 0.006%. So I'm good. Okay, so if that's X, that is also H plus. So they're asking for the pH. So that would be the molarity of H plus. So the pH would be negative log of 1.8 e negative 5, which is equal to 4.74. So that is the pH if you had a common ion in there. So you might wonder, well, I have no way to really understand what the common ion did. So what do you think we should do? Yeah, why don't we try doing it, see what the pH is if the common ion weren't there. That way we can see what the common ion did. Okay, so let's try it. So let's do the same equation, HC2, H3O2. Okay, pause the video and you can do this yourself. You're going to do the common ion if it was not added. Okay, so I'm going to do H plus C2, H3O2 minus, this is 0.30. If there's no common ion, so I just put 0, 0, minus X plus X plus X. So 0.30 minus X, X and X. Okay, so 1.8 e negative 5 is equal to X times X is X squared, making this negligible, 0.30. Solving for X, I get 0.0023. Solving for percent ionization, I got 0.0023 divided by 0.30 times 100, hoping that is less than 0.0023 divided by 0.30 times 100 is equal to 0.77. So that's less than 5%, so that's good. So X is the H. Okay, so this is molarity of H plus. pH is equal to negative log of 0.0023. pH is 2.63. Okay, so this is a 3. Okay, so this is the pH with no common ion. That means you didn't have anything in the beaker, 0 right here. That means it's just water. You put acid in water. The second one you put acid in. The first one we did here, you put acid. This is with acid with common ion. So which one's more acidic? This is more acidic. So what did the common ion do? Okay, let's write that down. Why don't you pause the video and try to tell me what the common ion did? You can write that down for yourself. So, the common ion prevented the acid from being too acidic. Right? It's not as acidic than before. So over here it's basic, this one is acidic. So the weak acid, the weak acetic acid, right, is even weaker than before. So what does the common ion do? The common ion prevents the acid from dissociating. Okay, think about walking in a dorm room. Let's say somebody's already in there, so you're gonna go, oh sorry, I can't be in there, somebody's already in there. The same thing with the acid, it can't dissociate because the ion is already in there. Okay, let's go ahead and do one more or two more practice problems. Go ahead and try this yourself. Pause the video. Okay, so it says calculate the fluoride ion concentration. So that means fluoride ion is F minus. That's what they want. And the pH of the solution. So they want the pH. So they want the H pluses, which is 0.20 molar HF. So what you're going to do here is you're going to write the equation for the acid. Okay, that's what you do first in these problems. And then what you do is you scan to see how much you have of each. You have 0.20 molar of this. And then what they will do is they will give you another number. Okay, and you're going to think, what do I do with that number? You have 0.1 molar HCl. When HCl goes into water, you're going to get all of it turning into H plus and all of it turning into Cl minus. The Cl minus won't do anything. So this number is pretty much just the H plus. So what's in the beaker is some H pluses already. Okay, now you think H plus is common ion to HF because when H breaks apart, you get H plus and F minus. So H plus is a common ion as well. And then you do your equilibrium, your icebox. So you see 0 here, minus X plus X plus X. So the presence of this common ion is going to prevent this HF from going to the right. It would rather go to the left. So you're going to go 0.20 minus X, 0.10 plus X, and X. Okay, so I'm going to call this one negligible. Okay, so Ka is equal to 6.8 E negative 4 is equal to 0.10, which is the amount of H pluses, and then X over 0.20, right? So X is going to be 1.4 E negative 3 molar, which is the amount of F minuses. And that is your first answer because they're asking for F minuses. Then they're asking for the pH. So the amount of H plus, remember you already had some in there. You already had 0.1 in there. And then you're going to add X. And X is what you solved here. So 0.10 plus 1.4 E negative 3. As you can see, it didn't really add too much because the HF is a weak acid and it made it even weaker by the common ion. Okay, so that so whatever that is, pH, oh sorry, H plus is equal to, so it's 0.10 plus that is 0.10, pretty much still 0.10. So pH is equal to negative log of 0.10, which is 0.99. So it's pretty much due to the HCl. The HF didn't hardly dissociated. Okay, let's try another one. It says calculate the formate ion. So you're going, what is formate ion? Well, they gave me formic acid, which is here. And remember, this is the H that dissociates. Okay, so the way you draw this is C, and then there's a double bond O, and then the O here. And then that's the COO, and then this H is on this side. And then this H is the one that comes off. Okay, calculate the formate ion and the pH of a solution that is 0.5 molar in formic acid. And some acid again. Okay, pause the video and do this yourself, please. Okay, in an effort to make this video shorter, so I wrote the equation here. You start with 0.05, you put it here. 0.1, because you have the acid, which is just the H plus, the NO3 won't do anything, so I put that there, and so on. I did that, and then I did the equation solved for X, which is the HCOO minus, which is this. And then for the pH, I added it to 0.1 plus the X to get the pH of 1.